Hi, my name is Chris Schulte, and today we'll be talking about lab number 1, the topic of charged tapes. The purpose of the lab is to prepare 2 charged pieces of clear tape and observe their interactions, performing an experiment to determine approximately how much excess charge is on one piece of the charged clear tape. The goal of the lab is to utilize a computational model of 2 charged tapes exerting electric force on each other and experiencing gravitational force, estimating the amount of charge on each tape necessary to float one above the other. Then, we are to recreate this computational model again, but instead using line charges rather than point charges. Finally, we are to compare the output from the computational models to the observations made on the pieces of tape. The fundamental physics principles and models used in this lab included Newton's second law, which relates the net interaction between the system and surroundings to the observed motion of the system. From this, we know that force equals mass times acceleration, and a system not in motion is in static equilibrium. This means that the net force in the system is equal to 0. We also utilize Coulomb's law, which states that the magnitude of the electrostatic force between 2 point charges is proportional to the product of the magnitude of the 2 charges and inversely proportional to the square of the distance between them. Here, we see the constant K, which is Coulomb's constant. Overview of results. The system in this experiment was tape A and tape B, and the surroundings was the Earth. We can see the experiment setup in the right of the screen. Results. Both pieces of tape had the same charge, positive, resulting in them repelling each other. The charge on each piece of tape is equal to approximately 1.28 times 10 to the negative 8 coulombs, and each piece of tape was determined to be deficient of roughly 8 times 10 to the 10 electrons. Data and analysis. Initial conditions. The U-tape is repelled by another piece of U-tape, but attracted to my hand. The U-tape was attracted to both a neutral table and a negatively charged pen. This indicates that the tape is positively charged as electrons were lost in this process. Tape length was measured to be 0.205 meters, and tape width was measured to be 0.0190 meters. Some calculations included the tape mass, which is calculated by multiplying 0.205 meters times 0.001 kilograms per meter for a tape mass of 0.000205 kilograms. The distance between the pieces of tape was measured to be 0.0271 meters. Then, to calculate the force of gravity, which is equal to mass times acceleration, I determined its value to be 0.00201 newtons. Since this system is in equilibrium, the electrostatic force is equal to the force of gravity. So, the force of gravity is also 0.00201 newtons in magnitude. And from this, we calculated the measured electric charge, which is 1.28 times 10 to the negative 8 coulombs. To calculate the deficient electrons, I took the tape charge and divided by the electron charge to get a value of 8.0 times 10 to the negative 10 deficient electrons. The number of atoms on the tape was calculated by taking the area of the tape divided by the area of the atom, which was 3.895 times 10 to the 17th atoms. The ratio of the number of deficient electrons to the number of atoms on the surface was 1 electron for every 4.87 times 10 to the 6 atoms. Here we see the computational model for the single point charge. To the left, we see our initial conditions and the calculations necessary to determine that one piece of charged tape has a charge of 1.28 times 10 to the negative 8 coulombs, and that for every 1 electron, there are 4.87 times 10 to the 6 atoms on the piece of tape. On the line charges computational model, we see that it is different and that we have a resultant vector of all the charges on the line of the tape to produce a net electric charge that is still equivalent to the downward charge of gravity. From lab 0, we see our E-field calculations as well as our initial conditions. Conclusions. Some main takeaways from this lab included the relation of Newton's second law and Coulomb's law, and the fact that the system was in equilibrium with 0 net force to calculate the charge on each piece of tape. We're also able to know that the charged tape was positive because positive charges repel one another, like negative charges that repel one another, and a positive and a negative charge attract one another. Assumptions. In this lab, we said that error resistance is negligible and that long tape pieces are treated as a point charge with all charge concentrated at the center for the first computational model. The mass of the tape was assumed to be 1 gram per meter, and the tape was considered completely neutral until charged by removing it from the base. For the floating tape, Fe and Fg were in equilibrium and no other forces were acting on it. Since all the above were assumptions and idealizations made, there is likely a slight error in the calculated charge of the piece of tape despite controlling as many variables as possible and being precise in measurements. What if? If the charge of the tape were reversed, there would be no change in the behavior of the tape. Given that both pieces of tape would now be positively charged, they would still repel each other since like charges repel. Additionally, we would see a loss of protons rather than electrons during the charging process. Why? The 2 values for Q that I obtained with the point charge computational model and the line charge model were indeed different. This is because the point charge model depicts the pieces of tape having their charge concentrated at one point at the center of the tape, while the line charge model shows the charges distributed across the piece of tape. The value obtained from the line charge model is more likely to be closer to the real value because it more accurately depicts the charge distribution of the pieces of tape. Thank you.